All right, thank you everyone for your patience. We made everything work. So today we have a speaker, LPL alum, Robert Zellem. You graduated, got a PhD from LPL in 2015.
Yep.
And he works on exoplanet atmospheres and in JPL. Now we welcome Bob and here.
Yeah, thank you so much for having me. Really appreciate it, everyone. So I'll be talking about one of the two major projects that I work on at JPL today. I also work on Roman CGI. I'm on the project science team, and unfortunately, Ewan's had to deal with me a lot on that. So apologies, Ewan, having to deal with me for all these years. But if you want to talk about direct imaging and Roman CGI, we have an upcoming call for a community participation program where you can actually submit your ideas to help work on the mission and develop it as well. So always happy to talk about direct imaging. Today I'll be focusing on sort of motivating why we need small ground-based telescopes. A lot of places love their large observatories. U of A is not without exception. You have many amazing opportunities and platforms here, from MMT to LBT to VAT to, there's so much telescopes out here. That's why I was always excited to be a graduate student here. But I used a lot of time on the smaller ones, specifically the 61-inch Kuiper telescope. It's really rewarding to use that telescope and get a ton of time and to do really impactful, high precision science with that, and also freak out because every bump and thing that you heard in the middle of the night, you thought it was Gerard Kuiper's ghost because he's buried up there, I think, underneath a rock. Yeah. So what I specialized in grad school here was observing from the ground, using telescopes like the 61-inch, like using Palomar, using Spitzer as well, and ground-based telescopes are always near and dear to my heart, because that's what got me really into astronomy when I was a kid. Let's see if my laser pointer will work. Oh, that's fine. Oh, because that's why. All right, I will click. All right, I know that we have some folks on the line who might not know what a transit is, so if you do, just bear with me for a minute. A transit is when, if you're observing a host star, and if you're really lucky, that star will have a planet around it. And if you're even more lucky, the geometry will just be so right where a planet will pass in front of the star, blocking out the star's light, causing the star to appear to dim momentarily. At best, this dip in brightness is typically in the order of about 1 to 3%, and it's really important because it gives us the planet to star radius ratio. So it tells us how big the planet is relative to its host star. What's really great, though, is also allows us to study the planet's atmosphere. Look at the transmissivity of the atmosphere of the planet as it blocks out the star's light. You can use Beer's law then to back out the molecular composition of the exoplanet itself. And it's been one of the main workhorses for discovering planets. It's found of the currently known 5,000 exoplanets. It's been used to discover about 3,000 of them. And you can actually do this pretty cheaply as well. I saw a Reddit post a few years ago where someone used a single DSLR camera for a really basic barn door tracker. They were able to observe an exoplanet. And what we're finding today is to do impactful science-grade observations, you only need scopes as big as 4 inches. Really small telescopes that are very affordable that anyone can use across the world. And I would argue that the transit method is actually here to stay. For the next few years, if not the next few decades at least. The transit method has been used very successfully by Hubble, for example, to characterize the atmospheres of about 50 exoplanets by looking at their water composition. James Webb, which is just doing amazingly, I'm so happy it's working out so well. Due to its increased primary mirror, due to its increased wavelength coverage, James Webb every new paper is revolutionizing the field. We're finding molecules we've never found before, at precisions we've never envisioned before, which is incredible. And we'll be looking at potentially hundreds of exoplanets using the transit method of James Webb. Beyond that, by the end of this decade, there's a European Space Agency mission called Ariel. This is a dedicated mission that will be looking at up to 1,000 exoplanets and characterizing the atmospheric composition and structure of these planets. And I would argue, beyond that, the next generation missions will also be continuing to use the transit method. So for example, the HABEX-LUVOIR hybrid that was recommended by the Decadal, I know that they have in their science cases also the opportunity to transits as well to look for biosignatures, in addition to using direct imaging methods. So the transit method is here to stay to continue characterizing the atmospheres of these exoplanets. But in order to observe these transiting events, we have to know very precisely when the transits will occur. So if I have my favorite exoplanet, I write a proposal to NASA for James Webb or Hubble time. I say, hey, I'm Rob, I'm not a complete idiot. Please give me some time on my favorite exoplanet, please. I provide them with an ephemeris, a prediction of when that next transit will occur. A lot of these planets, though, have very imprecise or not well-known transit times, and they can be uncertain on the order of minutes, sometimes hours. It doesn't sound like a lot of time, but if you start applying that average uncertainty to missions like Ariel, 5 minutes times 1,000 planets, that's a lot of time. Also, 1 hour on James Webb is about $1 million. If you look at the cost of James Webb and then convert it into its 7-year mission lifetime, it's really expensive. And these resources are very precious and few and far in between. You want to maximize their science. We don't want to waste their observing time. So if I have a very uncertain ephemeris, I can do one of two things. I can extend my observing campaign and sit on them longer with Hubble. Again, that's a waste of time. You're preventing other interesting science from happening. You're not using these very precious resources efficiently or effectively. Or you can do what we're now doing, which is to have a ground-based survey to update the transit times of these targets so you can make more accurate predictions and use these large observatories a lot more effectively. And roughly right around when we were sort of freaking out about this problem, because there's a lot of time and uncertainty that's built up over large planet catalogs, on the 100 to 200 to 1,000 planet catalogs. We were also working with some data from a small telescope called the Micro Observatory. Over at Mount Wrightson, right down below from the MMT, it's a really small 6-inch telescope that's fully robotic, fully weatherproof. It doesn't have calibrations. We didn't do flats, we didn't do darks, we didn't do biases, doesn't have perfect tracking. The stars look a little oblong over their 60-second exposure times. The target, in our case, wandered over the pixel array by 200 to 300 pixels. Despite all those issues, we got really beautiful, beautiful data from this telescope. And this is a 12th magnitude, 11th, 12th magnitude host star, about a 2 to 3% signal. And our brains started working here, and we're like, hey, if we can get amazing data that's science grade, I can claim that because we published this, then what happens if we start opening the door to many amateur astronomers? After giving talks, especially here in Tucson, I was a graduate student, I'd have amateurs come up to me and say, hey, your science is cool, how can I help out? I have this sort of telescope, and I didn't have a good answer for them. And this was sort of all culminating together. The issues of the ephemerides being stale, the idea that you can do really impactful, high-grade science with small telescopes, but also getting the amateur astronomer community and also high school students, college students, graduate students as well, involved in the science in this project. And that's what led us to launch a project called Exoplanet Watch that I'll get to in one quick second. But we did a further deep dive onto what a small telescope could offer. So we looked at at the time in 2020, the current planet list of the 4,000 at that time known planets. And we just basically forward estimated the data from that single microobservatory, actually a few microobservatory data sets. And we estimated that a single 6-inch telescope can detect at 3 sigma over almost 200 planets. So it's almost a planet a night, a random 6-inch telescope could observe. Also, you can detect a bunch and get a lot of information about their mid-transit uncertainty. And the 6-inch telescopes can actually start to probe planets that have very large ephemerides uncertainties as well to help improve their orbital period and their mid-transit times. We then ran some forward estimates and sort of said, okay, here's our currently known planets. Here's their published ephemerides on the NASA Exoplanet Archive. Let's forward propagate their uncertainties to 3 different missions. The launch at James Webb, the launch at Ariel, and also the launch of an Astro 2020 decadal that we launched, I think we did for 2030. Then we said, okay, here's the uncertainty of these times. Let's pretend now that we observe these targets with that same 6-inch scope out here in southern Arizona. How much time could we save? And we found we could save with a single 6-inch scope up to 10,000 hours, or 10,000 days, sorry, even worse than that. There's a lot of uncertainties in mid-transit times, really, really bad. But if we then also upscaled that to a larger campaign, actually relatively modest here. If we included 16 amateur astronomers or 16 small colleges and universities, each with their own 6-inch telescopes, we could save a considerable amount of time with that. So it's pretty amazing how impactful these small telescopes can be. Typically telescopes that people, haven't really looked upon other than making maybe a pretty picture on the internet once in a while. So you can do extremely impactful science-grade observations with a single small telescope. And then if you talk to a lot of these amateur astronomers, they typically have scopes 8, 10, 12, 16 inches. Some of them even have like meter class telescopes, especially in this area, this neck of the woods. Or if you're lucky to hop on something like that or WIN, you can absolutely do amazing precision work and really give back to the rest of the community to use these resources a lot more efficiently. So this not only impacts exoplanet science, but also the rest of the field of astronomy by really trying to use these scopes as efficiently as possible to eke out as much science as possible as well. Other science cases that we looked into, we go more into detail in our 2020 paper, but we also considered what the impact could be by looking for transit timing variations. Some solar systems, they'll have multiple planets in them, and the inner planet might have like an orbital period of like 3 days. But if there's an outer planet in that system, that'll gravitationally tug on the inner planet and cause this mid-transit time to fluctuate back and forth, kind of like a sine wave. And you can use that to infer the existence of that exterior planet. So there's a lot of effective work that can be done that you need long baseline observations. So a lot of people will say, well, TESS can figure out these ephemerides pretty accurately. And it can. TESS is doing amazing work. But there's a lot of planets out there that don't have a very long multi-year baseline, preventing you from looking for longer orbital period companions. Also, very importantly, we can monitor for stellar variability. And this has been done a lot. For example, there's the APT out here in southern Arizona. But we use this a lot and have used this a lot on assessing the impact of variability on Hubble and Spitzer measurements. The reason we care about variability so much is because if your host star is variable, that can drastically alter your interpretation of the exoplanet's atmosphere. A planet that you thought is hazy could be clear, a planet that you think is clear could be cloudy, and that has extremely impactful interpretations on the molecular mixing ratios of these planets. So we actually used some data from the APT to place limits on the variability of this host star in this specific study done by Brian Kilpatrick in 2019, where we said, okay, we see variability of the host star, we also see potential variability of the planet. And we were able to estimate the impact of variability of the host star and say, tentatively, that the variability we're seeing in Spitzer from eclipse measurement to eclipse measurement was real. Because, again, the host star's variability impacts your measurement and understanding of the planet's atmosphere as well. So variability is becoming very, very important. You probably all remember when Ben Rackman was here and doing tons of variability measurements in Daniel Pai's group. That was important for Hubble, and that's going to be even more important with James Webb as we have higher and higher precision measurements where variability becomes much more impactful and interesting. You can also use small scopes to look at blended pairs as well. As you're probably all aware, TESS is doing amazing work discovering tons of planets. But in order to observe the entire sky, TESS has very large pixels as projected on the sky. So a star that's actually 2 looks like 1 in a TESS pixel. And what this does is this basically biases your estimate of the planet's radius. A planet, due to the extra flux due to a neighboring star, the transit depth will actually decrease in its flux. So a planet that's actually a Neptune-sized object or a Jupiter-sized planet, you actually might wrongly interpret that as being an Earth-sized or super Earth-like planet. Here's actually some data from the Micro Observatory. Here's some 2 stars. You can sort of see that potato oblong shape due to the imperfect tracking. Despite that, you can clearly see it's 2 stars. But if you then downsample that to the TESS spatial resolution, that looks like 1 star, and that can alter your interpretation of the planet's atmosphere. Again, impactful science that can be done with a single 6-inch telescope. So at the end of that 2020 study, we said, oh, we should probably start doing something about this. So we launched this citizen science project called Exoplanet Watch. Exoplanet Watch was started about 3 years ago, like in 2019, really started hitting our stride in 2020. Then something happened in spring of 2020, maybe for about 2 years, and now we're getting our feet under us again. Luckily, this has been mostly completely virtual international project. So luckily, at the end of the day, we're minimally impacted by COVID, thankfully. What Exoplanet Watch does is we have, since it is a citizen science project, we're trying to include amateur astronomers, folks in colleges, universities, high schools, anyone that wants to get involved in exoplanet science. Unfortunately, there's a perception out there that you can get a giant telescope and dark sky conditions to do science-grade observations, and that's not the truth. Yeah, sorry, do you have a question?
Yeah, that's exactly what I was wondering about. Obviously Mount Hopkins is wonderful, but people are in cities with, aerosols and all the rest of it. Okay.
Yeah, we have a user that's 2 towns to the east of me in Los Angeles, and he's given us 250 measurements of exoplanet transits. So despite him being in suburban LA, he's making amazing transit observations. His scope is about a 16-inch scope, so a little bit larger. But he also had an undergrad who took a 6-inch celestron off the shelf with an Ioptron equatorial mount and a really cheap $200 ZW Astrocam, hooked them all together, took it to the roof of Caltech, downtown Pasadena, horrible light pollution. It's next to an athletic field, much like you have here at U of A. Still able to make and published his results in our paper last month, actually. He contributed to a global campaign that I'll be talking about a little bit later. So you don't need a big scope. You don't need dark skies. You don't have to have a physical or like a permanent observatory. This science is a lot more forgiving than people realize, believe it or not. But we have these 2 goals that we're trying to always shoot for. We have the education goals to increase folks' identity as scientists, to hopefully also get the next generation of scientists involved in becoming astronomers at the end of the day, and increase their confidence about their ability to do science. We also have all those science goals I just talked about in the previous slides. I'll save a breath and not say them again. But if you have questions about them, I'm happy to answer them as well. And that's what got us to start Exoplanet Watch, is this campaign to get anyone and everyone, not just professional astronomers. We have a ton of school groups already involved in this project. We have professors including this as part of their curriculum for their classes. And there's students for leading first author published papers as well that are getting cited. Also amateur astronomers and anyone and everyone. I'll talk about this a little bit later and how we're getting the general public involved as starting this January. But it's a completely collaborative effort to complement existing surveys. So for example, there's ExoClock. It's basically the European version of Exoplanet Watch, but they're trying to update the ephemerity specifically for aerial. And we're really friendly with those guys. I get beers with the guys when we have conferences together. And we actually help with some observing campaigns as well. We work a lot with planet hunters to help confirm their candidate planets. We're also a member of the TFOP SG1, so we're full members of that as well. And also Diana Dragomir and Paul Dalba, and I'm forgetting someone else, their single transitors group as well. All of our data is immediately public to the entire community. There's no proprietary phase. We update our system every 2 days, every other day. And there's no proprietary phase. All of our data is out there and freely accessible for anyone to download. And if I have time, I can show you a results page, but you can also go on our website. All of our data products are there. We show all of our posteriors, we show our data quality, we sweep nothing underneath the rug as much as we can. We try to make it also easy for anyone to go on our website and download the data to use as much as they want. We also have an opportunity for community feedback. We've had some professional astronomers come to us and say, hey, here's my favorite exoplanet, can you help me observe in this campaign? We had 2 big campaigns, one in November. I think it's the longest transit duration that's been ever observed from the ground. And also one in December in support of some James Webb observations that will be happening this fall to update its ephemeris. Also, one thing I'm really proud of is that observers will be listed as co-authors on any published results that haven't been published previously. If the amateurs, astronomers, if the high schoolers, college, graduate students do the work, they deserve the credit to be listed as co-authors. And we're funded, it's a little blocked here in the room, by NASA's Universal Learning. This is a EPO group funded by NASA SMD. And we're funded actually through the end of 2026, and hopefully we'll get funded again beyond that. So the plan is to be around for a long time and to make this data accessible to the entire community. So we're actually a really small group of folks, and none of us work on this at full time. Any of us work on this is like 40% of our time. We have three amazing interns. We have Isabella Huckabee at ASU. We have Kaya May at UC Boulder. We have Tamim Fatahi, who is an undergrad at Cal Poly Slope. And then we have 5 JPLers on it as well. We have Nora, John, Kyle Pearson, an LPL alum, who's now one of our Python code gurus. Rachel, and myself as well, this weird character on the right. And it's been really great to have to do that mentorship on this project. And our interns contribute so meaningfully in such a major way to this project. It's absolutely incredible. We're absolutely lucky to have them. That being said, we're always looking for summer interns. So if you know of any interns that would like to work on this project, please let me know, because we'll start to look at their applications starting in January. So please do reach out as well. So I'll quickly run through the user experience here. The first step is you plan your observations. You can use any tool you want to. The NASA Exoplanet Archive has one. I personally use the Swarthmore Transit Finder. If you haven't used that before, it's extremely user-friendly. It shows you air mass plots, it shows you all the objects that are visible from your specific location on the Earth. They also have our Exoplanet Watch target list. We give them a prioritized target list for them, and they actually host that for us as well. Then you go and observe your exoplanet. You can observe whatever you want. We don't care. You can observe a target that everyone's been observing, like an HD 209458b that we've been observing for the last 25 years or so. Or you can observe something that was just discovered yesterday. We don't care. Upload whatever you want. Observe whatever you want. The data is extremely helpful because we can still place limits on planetary companions by looking at TTVs over long baselines, for example. Here's actually a really cool photo that one of our users, Doug Lalla, took. He was observing 189, which is right there, hot Jupiter around one of the brightest host stars. And he's also doing astrophotography simultaneously. So he got a really cool picture of the Dumbbell Nebula while he was getting a nice light curve. And it's really funny because we have a ton of amateur astronomers in our project that are just blown away they can observe transits. And they also upload their astrophotos to our Slack channel. I'm blown away at the cool astrophotography images because I was horrible at that. I could never do that. And it's kind of funny because I'm like, oh, yeah, transits are simple. And it's kind of funny because if you can do astrophotography, you can do transits. Or if you can't do astrophotography, i.e. me, you can still do transits as well. The data taking and observing is actually very forgiving. Right now, we've launched out to professional astronomers, that's why I'm here, and also amateur astronomers, folks who have their own telescopes. But starting in January, what we'll be doing is launching out to the general public. We'll no longer make it a requirement that you have your own telescope. The Micro Observatory actually has about 10 years of archival data just sitting in their hard drives. We have 2 telescopes I'll talk a little bit about later that I'm commissioning right now in the Los Angeles area that we're going to make robotic and observe new transits every single night. Then we'll actually give this data out to our users so you no longer need your own telescope to participate in this project. Check out or borrow some of our data as well and still meaningfully contribute to this project. Then, after you do your own observations or get your own data from a robotic telescope, you analyze your own data. We didn't want people to have to take their own images and upload it to some random cloud black box. We wanted our users to be directly connected with the data analysis and reduction methods. We have our own analysis tool, which I'll talk a little bit about later. You can also use whatever you want. Tons of people use AstroImageJ. Rachel probably has like 5,000 Python codes that are doing this right now. Maybe on some test data. You can use whatever you want. Don't care. You just have to report to us at the end of the day. The JD, flux, a flux uncertainty, ideally, but we can also estimate that ourselves, and the air mass. Just give us those 4 values, you're good to go. You then upload your data to the American Association of Variable Star Research. Observers. The reason we're partnering with the AAVSO is because when we were trying to think about how our users get their data to us at JPL, we were freaking out. For some reason, JPL doesn't like random people uploading data to JPL servers. I don't know why. So we were like trying to make this convoluted way of doing like drop boxes, and it was a mess. I contacted the AVSO because I wanted to get their observers involved in our project, and they just like sort of offside said, "Oh yeah, we have our own database and you can use it." And I was like, "Thank God." That truly saved us, and it was perfect timing. And they let us use their database for free. And the AVSO, that's why I'm actually in town, is they had their annual meeting this past weekend, and they've been an absolute pleasure to work with. They have this database. They've been giving us many of our hundreds of initial users. And thanks to them, we have actually bypassed or surpassed all of our milestones a year in advance, which is incredible. I'll talk a little bit about that later as well. So once you upload your data, you just sort of sit back, relax, pop a few beers open, maybe polish a paper, or you can also go on our website and look at any of our data and data products and publish any of your studies that you want. If you have your favorite exoplanet, go on our website, take a look. If you see data that you need or want, go for it. I hope you scoop me, kind of and not kind of. I don't like writing papers, so go for it. But the only thing we ask in return is you cite our paper and then you write a little acknowledgement statement. And then if you use any data that hasn't been published before, you reach out to those amateurs and offer to make them co-authors on your paper. Again, if they do the work, they deserve the credit. Actually, this is a screenshot from our 2020 paper where we sort of demonstrated the capability of single 6-inch scopes and a small 16-scope network of 6-inch scopes. And about half of these folks that are co-authors in this paper are high school students and amateur astronomers, which is absolutely incredible.
So Rob, you have a question.
Yeah.
Actually, Colette is asking, can you share a link for the summer internship after this talk? So it was that question, but could you share that one so that everybody can see it?
Sure. So for the summer internship opportunities, I would Google, I think it's JPL summer internships or JPL education. I think the website officially is jpleducation.jpl.nasa.gov, something like that, or internships or intern. If you search those words on Google, it should pop up. And on there, you can put in your CV, your resume, and then put yourself in the pool, but then also reach out to me directly too. And let me know if you're interested or have a student candidate that you think will be interested in working in this project. And then in January, we'll start interviewing candidates. So that's always through thanks to recommendations by some people. That's how we got 2 of our 3 summer interns from this past year, and they've been absolutely, strongly pun intended, stellar. So yeah, thanks. So that's the user experience. That's if you wanted to become a member of Exoplanet Watch or contribute your data that's just sitting on your hard drive, or even data that you might have published that hasn't made its way into the NASA Exoplanet archive. You can upload your old light curves, even if they're years ago, like they were taken in 2006 or 2001. We still want your data because it gives us very helpful information about these TTVs and about long-term stellar variability. On the back end, we have this pipeline called Citizens. This is an acronym I can never remember, so that's why it's misspelled. It's a really clever acronym, but I can never remember what it stands for. But what Citizens does is it goes out to the AVSO website every other night and it downloads all the data. We then reprocess and refit the data, basically with a slightly tweaked version of Exotic. The reason we reprocess or refit the data is because we want to update the light curves in their priors. So if some new values come out from the archive, they fix or update stellar radii or ephemerides or inclinations or metallicies, we can still keep those light curves that were taken days, months, years ago. We can still keep them relevant and up to date just by changing our priors. Then we immediately publish all of that on our website. Again, no proprietary phase. We're trying to democratize and open up this science so access to data and to telescopes is no longer a limiting factor here. So I've been talking a little bit about Exotic and alluding to it a little bit earlier. And what Exotic is, it's a fully Python 3 code that takes your raw FITS files and does your full calibrations and your full analysis on it as well. Exotic will figure out your optimal aperture of your extraction circle for extracting photometry. It determines the optimal sky annulus for doing the sky background estimation. It'll also pick out your ideal comparison star as well. We don't use a blend of comp stars. We do the best or none at all if it actually adds to the scatter of your data. The reason for that is I don't like having a blend of comp stars because it's very difficult then at that point to say that you actually included a variable star in your comparison stars. It makes it more difficult to trace those errors through and see which of those comparison stars is contributing to that error. And then Exotic will also do a fully Bayesian, statistically significant model fit to your data. And this is what really sets us apart of other data analysis and reduction codes. This will fit your data with a nested sampler, Mandel-Nagel-esque light curve, and give you faux posteriors and uncertainties at the end of the day, and that you can actually publish in a paper. It'll give you your posteriors, your triangle plots, or your stair pairs. It'll actually give you uncertainties that you can actually trust as well. You can see that because we published that in our paper in 2020. It also gives you helpful diagnostic plots such as FOV plots for field of view, which is really important for doing test follow-up. It also gives you other diagnostic plots like the error mass, the change, or the correlation between your flux and other systematic error sources. This also corrects for error mass, and this has been used on probably 75% of all the data that's been contributed to us so far. Exotic also has this really cool data reduction, real-time data reduction software feature as well. This is actually completely born off of our time at the 61-inch. Sitting up there at the 61, transit observations are really boring. And it's good when they're boring, because that means things are going correct. Otherwise, you're just sitting on a star for 5 to 6 hours, right? And we're like, this is boring. Can we make sure that we're doing what we're supposed to do, that we're actually looking at a transit? So Kyle made this really quick and dirty analysis that does the flux extraction, so you can see the transit happening in real time. And we actually use this code today at Palomar to make sure that we're observing the right thing at the right time on the 5 meter. It also helps you stay awake at 2 o'clock in the morning. You see a transit tip occurring. What's really cool though is if you do a star party, observing again a transit by eye is boring, and seeing that 1% flux drop is very difficult to see by eye. But if you have your computer hooked up to your telescope and are running Exotic, you can point to someone that's passing by your telescope, your computer, and you can say, hey, we're observing an exoplanet that's blocking out the light from its host star and casting a shadow on the Earth hundreds of light years away. So there's that opportunity to engage the public as well, while you're also doing meaningful, impactful science. This also takes only about 4 minutes to run and does your complete analysis, also do your calibrations for you as well. So we really tried to make it as user-friendly as possible to run, but also as fast as possible to run. It runs on Windows, Macs, and Linux computers as well. But also, we just launched 3 new versions of Exotic this last Monday, a week from today, last week, that run fully in the Google Colab cloud. So it runs completely in a Python notebook, and it runs on the free Google servers. So you can actually run Exotic on your mobile phone. You don't need a powerful Mac or any powerful computer to do this. You can use a Chromebook because it all runs on Google servers. You just need a free Google account. And then what we'll be doing is we'll be sharing this data with our users via Google so they can also do their own analysis themselves on their own data from a robotic telescope. I think, Rachel, you also use Exotic as well to do light curve fitting on tests. You can install and import Exotic's modules as well. So if you wanted to do a nested sampler fit to your transit data, you wanted to maybe bypass the other photometry, you can jump in and give Exotic some pre-reduced data and do statistically significant Bayesian fits to your data as well. So thank you, Rachel, for using Exotic. All right. So how do you get involved in this project? Hopefully I've gotten you all excited enough to want to do that as well. So currently, we've only launched out to people that have their own telescope. Last summer, we did a big push towards amateur astronomers. This current year, we're working on professional astronomers to make them aware about this community resource that we're doing, but also to get professional astronomers that have access to their own telescopes, particularly small telescopes, to use those resources and help contribute to this project and also turn it into research projects for their students as well. We are working on right now getting access on a grander scale to robotic data as well. Here's actually a picture of the micro observatory here on Mount Wrightson. I think, yeah, MMT is this way, maybe? But this operates rain or shine every single night of the year. And it's actually really cool. You can actually see some clouds occasionally passing into view. And they have 10 years of archival data, hundreds upon hundreds of data sets. And what we'll be doing in 22, January, is we'll be setting up a library checkout system to automate the checking out of data as well. One of my main mantras in this project as the project lead is to have or minimize the human in the loop as much as possible. I like sleep. My wife also sometimes tolerates me, so I prefer not to work on nights and weekends. So we've tried to automate the system as much as possible. So if I, God forbid, go on vacation, the project doesn't die without me there, which is nice. So we actually have a way where users can contribute their email address and our system will automatically assign them a data set. They have 2 weeks to do something with it. If they don't, that data goes back into general circulation. If they do, submit the data, congratulations, you get more data to work with as well. So again, this is removing the barrier from having access to a telescope, which not everyone can afford, because they can be very expensive. They can be $1,500. Really trying to remove that as a requirement for participation in this project. We're also working right now on commissioning some telescopes. We're actually renting out 2 telescopes at a facility called Table Mountain. Table Mountain is actually an observatory owned and operated by JPL. And they have this 0.4 meter telescope. I'm actually showing it right here in this picture. And this is located in Wrightwood, California. It's part of the San Gabriels. If you've ever driven between Los Angeles and Las Vegas, after you cut through the mountains, it's on your left. I see the observatory there. And this is a 0.4 meter telescope. We affectionately call it Luke, giant Star Wars fan. So this is the first one that came online. Luke was the first twin to be born. So this one's named Luke. I'm a giant nerd, come on. Small 6-foot dome, can't even fit in there, but I can control this anywhere in the world. I was actually observing on this telescope last night from my hotel room here in Tucson. I was observing a transiting exoplanet last night. And we're working on automating this telescope and making it fully automatic. Right now it doesn't have a cloud sensor that's on order, thanks to supply chain issues. Hopefully that'll be coming in soon. And we'll be running this every single night that it's clear in Southern California to additionally give more data to our users. As well, this gives us a telescope that we can say to a professional that says, hey, can you observe this target? If it's observable in Southern California and we have a clear night, we can guarantee them data. But that's another great thing about this project is by having a large group of folks across the entire world, it really helps us mitigate weather issues as well. I'll be talking about that in a little bit in a second. We are also getting, so that's an actual picture from the webcam that's inside the 0.4 meter dome that was taken a few weeks ago by me. We also have a 0.6 meter, and this one will be called Leia. Second telescope coming online, second twin born, giant nerd. We also have a 1 meter telescope we'll occasionally use. We'll either call that Jar Jar Binks or Darth Vader, or maybe R2, I don't know. We haven't figured that out yet. But this 0.6 meter will be coming online hopefully in the next calendar year, so in January. So we'll have 2 telescopes, a 0.4 meter, a 0.6 meter that we'll have full control over. We'll have the micro observatory, which is also dedicated to looking at transits. And we work very closely with the micro observatory at Harvard Smithsonian as well to provide data. So we'll have hopefully hundreds of data sets, if not thousands, to have accessible for our users. We can also get a lot of science out of as well. We also have our website. We've been doing a lot of redesign on that. It was originally written by me, and it was definitely written by a scientist. There's just lots of words and not a lot of pictures. We've been doing a lot of work on increasing the UX, the user experience. We have a monthly newsletter. You can actually sign up for our newsletter on our website. And we also have our Slack channel that's really awesome and active and a great way to communicate with our users. They can Slack me. I think they're actually doing it right now because my phone is vibrating right now. You can actually reach out to any of us day or night on our Slack channel. I might not answer you because I might be watching football on Sunday, but you can also reach out to us directly as well. And actually, here's a meme that my intern is posting, Kaya, the morning meme that we usually have on mornings as well. So here's some current results, and actually these are already out of date. These are taken 5 days ago. These numbers are already out of date. We actually have, I think we've had about 5 new members, roughly 1 a day, the last 5 days. So we have over 700 members across 22 time zones, mind-boggling. We're covering most of the globe here. We actually now have 250 total targets on our pipeline. That's probably more because it ran last night. And we have, I think, closer to 1,200 total data reductions. For comparison, I was hoping to have 200 targets by the end of next calendar year. I'm already at 250 a year in advance. I was hoping to get 500 observations. We're now at almost 1,200. When we really kicked this project off about 2 years ago, we had 100 and maybe 5 planets. It's incredible how much this has grown thanks to our users. Our users are absolutely incredible. So today, we've only saved about a third of an hour. If you talked to me about 3 months ago, this number was more like 3 hours. The reason that's changed is because the ephemeralities have been updated and changed. We always scrape from the NASA Exoplanet archive. We always keep ourselves current and updated, so this number will continue to change. But again, 1 hour in James Webb is $1 million. So if NASA wants to cut me a check for 300 grand, that'll be awesome. And on our website, we show all the light curves, so we're very transparent about the data quality coming from our users. We also make our O-C plots as well. So we're trying to make everything as accessible and easy for any of you to grab, to download. There's a button to click to download all the data. There's another button to click to directly contact through the APSO the members to get their information, to include them as co-authors. We try to really make it as simple to participate and to use this resource. One thing we're really proud of, though, is, and this truly shows the power of having a large ground-based group of folks across many different platforms across the entire world. As we observed this transiting exoplanet called HD 80606b. This is one of the most eccentric exoplanets. Its orbit is about a 100-day orbital period, and this is being observed by 2 different groups on James Webb to understand the impacts on the atmosphere as the planet gets farther and closer to its host star. The problem is 80606's transit duration is 12 hours. It's impossible for any single user to observe the pre and post transit baseline and the transit in one single night. Completely impossible. But if you get tons of observers involved across the world, you can combine their data together. That's exactly what we did back in December. We have people in Japan who started observing the pre-transit baseline, passed it off to folks in India that started getting the first part of the transit. Europe got, I think, about mid-transit, and the US got the second half of the transit, and they actually passed it off to some people that observed it on one night, observed on the second night, and got post-transit baseline. And of course, most of the northern hemisphere was cloudy this night. If you look at cloud maps, it's one of the most depressing things you'll ever see. Clouds were everywhere. We probably had another factor of 2 to 3 more amateur astronomers that wanted to participate in this project, but were clouded out. So this is why you need such a big campaign spread across the world. So if it's cloudy in Tucson, it's hopefully clear in Texas or Southern California. And here's some of the data and the observers that contributed data as well. We had 24 facilities. The largest scope we had on there was a 0.7 meter, about a 30-inch telescope. A majority of them were small 4.5-inch telescopes, maybe like 12 centimeters or larger. Really small observatories. And if you look at the individual data, you might say, I don't see anything in there. The data quality is you might say it's dubious. But once you combine everything together and phase it all together, you get a really nice looking transit. And this target also had test data on it. And the test data alone wasn't sufficient to refine the ephemeris of this target. It wasn't until we included the data from our amateur astronomers that we were able to get a really good demonstration of the mid-transit time. I saw Kevin just asked if we have any Southern Hemisphere observers. We do. We have some in South America. We have some in New Zealand and Australia. And I really want to expand into Africa. That's traditionally a part of the world, unfortunately, that doesn't have a lot of observatories. And we'd love to increase our coverage of the world in that continent as well. So here's a really nice ominous C plot that Kyle Pearson, he was the PI of this program and wrote the paper that came out 2 or 3 weeks ago. If we use just the data from the NASA Exoplanet Archive alone, those uncertainties get very large with increasing amounts of time. What we were able to do is we were able to shrink down that uncertainty in transit time and save an hour of uncertainty of observing time on this target. And when you start looking at eclipses, the story is much, much worse. Folks typically focus on transits. The last published eclipse paper, I don't think has come out in a long time, at least maybe 3 years, or at least they've been very few and far between. So the eclipses themselves are even more stale with respect to the transits. And we're able to save a lot more time on our eclipse measurements for predicting that as well. And that's extremely important for James Webb and Ariel. Ariel wants to observe 200 eclipsing planets. We have a lot of work to do on these planets as well. And despite not fully launching, we still have a ton of publications. We have about 15 or 16 publications. Only 3 of these are written by actual professional astronomers. This weird dude Zellem here, 2019 and 2020, and Kyle's paper is right here in the middle. Most of these are actually high school students and some undergrads. They're getting data from the micro observatory and publishing their own data, their own results, getting their first authored publications in a ton of journals. You know, there's the JAVSO, free journal to publish your work in, and they're actually contributing back to the field even at the high school level, which is absolutely incredible. So I mentioned our student involvement. For example, Molly Simon at ASU, just up the road, will be talking there on Wednesday. She actually is teaching a class that actually uses Exoplanet Watch. And the goal at the end of her semester is to have her students publish a paper on a target they're studying in detail. We have people in San Diego, some in Australia, all across the US. We have Stanford Online High School, so high school students that are publishing a lot of those papers I showed in the previous slide. Canada, Queensland, so tons of people across the world. And I think also UN students last night were hopefully observing a LOS 10, the 61-inch. So I'll have to put UN, I'll have to put your name up here too if you allow me to. So that's sort of a really quick overview of Exoplanet Watch, our citizen science project to keep folks involved to monitor transiting exoplanets. Because really, there's so many planets that it's impossible for the professional community to do it on our own. We really need amateur astronomers to help us out, to help us get the coverage of the world. For example, that 80606 observations, if we relied upon professional astronomers alone, we would have not been able to do that study at all. We'll stop. The amateurs saved us because they were able to make high precision observations across the globe and minimize the impact of weather. You can contact us by emailing us at exoplanetwatch@jpl.nasa.gov. You could try to memorize that URL. The easiest way to do that, though, is to Google NASA Exoplanet Watch, and we should be the very top query of Google. I haven't tried Bing yet, so don't quote me on that. And we'd love to have you. And now, thank you so much for your time and your patience. I'm happy to take any questions you might have. Thanks, everyone.
Thank you, and I did Google it and it came out. So,
Perfect.
okay, any question from audience here? Chad.
So you've created quite a back end here, but I must have missed it at the beginning. How do we get targets into the beginning, and who's doing the vetting? I mean, TESS is a great example where it's producing huge numbers of official TOIs and tentative TOIs that are being kept secret by various groups, and we need follow-up observations of them. So how do we inject those targets into this so that the observations happen? Who's doing the prioritization? Is it you with an Excel spreadsheet sitting there trying to organize all of this, which seems like might blow up on you in 6 months or something?
Yeah, so we devised actually a figure of merit that ranks targets based upon the brightness of their host star and their spectral modulation. We devised this figure of merit and used it for the Finesse and Ariel missions, and we published this back in 2017 as part of a paper, and now other groups have used it as well to rank targets for follow-up with like James Webb or Hubble, or also other groups have in parallel been devising and thinking of similar ways to do that. We also added an additional term of the uncertainty of the mid-transit time. So it's done completely using this single metric. So there's not Rob always updating Excel spreadsheets. It's just me looking at the archive, running the code, and outs as the prioritized target list. That's then has been sent to the Swarthmore Transit Finder group, so it's very easy to find targets. But one of the most effective ways we've been able to get our users excited about a campaign for your favorite exoplanet is by me saying, hey, tonight this target is transiting in Tucson. I did that last night. Hopefully we got a few observations of WASP 10, which one of our undergrad interns, Izzy, at the ASU, is studying in detail. I'll be writing a paper about. You can also, we have bi-weekly meetings with our users and our community as well. Anyone is welcome to join in and contribute. And we've had professional astronomers come and give talks. You should give a talk, Rachel, to our users. And you can plug your science. They love it. They love hearing from professional astronomers and contributing and participating in science. That's another great way to do it too. So yeah, there's a ton of different ways.
Just so I can log it in my head, what rough magnitude does the figure to merit start to fall apart and tell you that targets don't get observed?
It doesn't care. So it basically it's a penalty term where it sort of estimates the signal to noise by converting the magnitude into a flux. And it's all relative, right?
So how faint do you go though, I guess?
We use the entire catalog, the entire 5,000 planet or the 4,000 transiting exoplanet catalog on the archive. And
So
we're
so you're only doing one planets from the exoplanet archive. They're not new, tentative, not yet published.
During this, we're focusing on the confirmed planets that are confirmed, yes. But since we are test SG1 members, you can also use our user group to help follow up candidate planets.
Okay.
There's someone on our Slack channel right now that has a candidate planet they want follow-up information on, and hopefully some of our users will help out as well. I'm always happy to help amplify people who say, hey, here's this cool target. I'm happy to at-channel everyone so all of our 700 members see it as well. Also giving the talks and giving a presentation, motivating the science. They want to learn more. They want to know why they should care about a target and all the cool science that goes behind it as well. And then you can use Exotic. It gives the output that SG1 needs. It has the field of view plots. It has the flux. It has the light curves. So you can then submit those to Karen Collins, for example, at SG1, and she can look at them and make an assessment of the data quality. Okay, thanks. Yeah.
We have a question from Mr. Cowell. Would you like to speak up? Unmute? Or should I read? Yeah, here we go.
I can try. Yeah. You mentioned that the Exoplanet Watch accepts mostly light flux data, and are there any future plans to extend that to spectroscopy data as well?
Yeah, that would be great. Spectroscopy of these host stars is something we're starting to think about. We actually just recently added a new feature into Exotic to also monitor for stellar variability of these host stars. So one of the two outputs that you get on Exotic is not only your transit light curve, but also a measurement, the flux of the actual absolute flux calibrated magnitude of your host star, and you can contribute that as well to the AVSO's database. I actually put out a big announcement through the AVSO to get observations of HD 189733b because there's some James Webb and Hubble programs that are happening right now. And I expect to maybe get like 20. There's like 1,500 observations of these targets that have happened in the last 3 months. There's a huge user group out there of folks that want to contribute and are excited to contribute. But spectroscopy is something we definitely would love to get into and start going to that field as well, because that'll give you maybe even more information about host stars and their makeup and their parameters, their properties. Yeah, great question. Thank you.
Rachel.
So I was wondering, so since I use Exotic, I was wondering if this feature is available or no. How do you account for flux contamination? How do the amateur astronomers that you work with account for flux contamination or transit depth dilution when they're working with the data? Do they just assume 100% flux, or can they use available AO data to say that, or Gaia data, for example, to make certain corrections to be?
Yeah, right now with Exotic, you have to do post processing. So, Dave Ciardi published, I think in 2015, a really handy, simple equation you can do if you know the flux ratio of your two stars. I actually did that for our 2020 paper as well. I sort of estimated by there. It doesn't then correct for the transit depth, unfortunately, but that is something we definitely look into, Rachel. But that's one of the reasons I recommend people sort of steer clear of the Kepler targets. A lot of the Kepler targets are in extremely busy fields. You need really good seeing to void stellar lens, for example. But that is something we can definitely add in. That's a great idea. So add an open issue on our GitHub, please, if you don't mind. But getting back to another question before is that, we're trying to keep this as automated as possible. Our pipeline, no human in the loop at all. It runs by itself. Everything is motivated statistically. Right now, we assess the quality of a data set by looking at its scatter, but also if they made a significant detection of a transit depth of a target. Then it goes into our OMIC plot, for example. We also run this every other day. It's impossible for me to look through 1,000 light curves every other night. So we really try to make it as automated as possible so it's scalable, but also still keep motivated by also looking at the population itself, looking at its nearest neighbors, using very much a strength in numbers play, but also leveraging the information we already have from the NASA Exoplanet Archive, the Hubble, by Spitzer, by James Webb observations as well.
Okay, one last comment. Hannah Tanquary says, great talk, Rob. I vote for Jar Jar Binks.
Thanks, Anna. Appreciate it.
Okay. Any other question? Okay, thank you very much, Rob.
Yeah, thanks again. I'm here today, so I think I'm pretty free this afternoon. So if you'd like to meet with me, you could also do it over Zoom or WebEx. Just send me an email or reach out. Thanks everyone for having me. Really appreciate it.
Thank you.